my dear friends, welcome to IMS Academy. I am Sourav Upadhyay and I welcome all of you to this live session of the fundamental series that I have started 2 days back. So my dear friends, we have started with the subject of strength of materials, and in the first 2 lectures, let me give you an overview. I have discussed the concept of stress and then I have discussed the concept of strain. As far as yesterday's lecture is concerned, I discussed the concept of normal strain. I discussed the concept of shear strain, how they are measured, shear stress equilibrium, and also we did questions regarding to the topic so that you get a clear idea about the topic. Sorry. Just a minute. So what we are going to do today? What will be the agenda for today? So today we will continue, as I said, that we'll be starting with a question of shear strain, and then we will see what is Hooke's law, and finally we will conclude with the topic of deformation in an axially loaded member, right? Okay. So without wasting any time, let us quickly get underway with this question. Please read the question and then we will discuss. So what the question says? The question says that due to a loading, the plate is deformed into the dashed shape as shown in this figure. Just ignore this one, just refer the figure. Determine A, the average normal strain along the side AB, that means along this AB side, and B, the average shear strain in the plate at point A relative to X and Y axis. Okay. So my dear friends, what was the formula for average normal strain? So average normal strain along any axis, so let's say for AB will be the final length minus the original length divided by the original length. So let's say original length you can see AB, and the final length I can say as A dash and B dash, where A and A dash are same only. Or you can just ignore A dash, you simply refer A only. You just ignore A dash, so I should write AB dash minus AB divided by AB. So AB you know, but first we have to calculate the dimensions of AB dash. Okay, so AB dash, how to find out? This is it. So I need to calculate AB dash. So this distance is given as 3 mm and this height is given as 250 minus 2, that is 248 mm. So what will be AB dash? So AB dash will be root over 248 square plus 3 square. So if you find out, this will come out to be 248.018 mm. And once you know AB dash, so very easily I can calculate what is the strain in AB. So strain will be 248.018 minus the original length is 250 divided by the original length is 250, and once you find out, this will come out to be minus 7.93 into 10 to the power minus 3. If you want to write in meter units, so you can write mm per mm. So why the negative sign is coming? The negative sign is coming because contraction is taking place. Why the negative sign is coming? So negative sign is coming due to the contraction. Right. Good evening, mechanical world. Okay. And now we have to find out what is the average shear strain in the plate at point A. At this point, we have to find the shear strain. So you know that shear strain is nothing but the change in the angle with respect to two perpendicular axes. Initially, AC and AB were perpendicular to each other. Initially, the angle between the two is 90 degree. But now you can see that the angle has changed to some theta dash or some theta. So this angle gap, the change with which this is taking place, the change is nothing but the shear strain. I hope I am clear to you. So I should show you here itself that let's say this angle I am taking at gamma, this angle is gamma. So tan gamma, I should write tan gamma, over here I am solving, is this length BB dash, this length BB dash is 3 divided by this height. So tan gamma I have to find out, tan gamma is 3 by height is 250 minus 2, so 248. So gamma, if you ask me, it will be tan inverse 3 by 248, and if you solve this, if you solve this, you will be getting 0.0121 radian. If you solve this, you will be getting 0.012 radian. As you know that we should keep our answer in terms of radian. Okay. So, so I hope this question is clear to you. And yesterday, whatever we discussed, the concept of shear strain and normal strain, I am able to explain you neatly. Okay. Now let us move to a new topic. Okay. So this has been our course flow, that I will teach you one topic, and when we have studied that topic from the basics, then I will also solve one question. So let us now see some concepts. So now, my dear friends, what is Saint-Venant's principle? I'll try to explain you, but you first see this figure. Please see this figure once. Over here, if it is visible to you, when the load is applied, clearly you can see that some deformation is taking place. Some localized deformations is taking place over here. If this is clear to you. And also, suppose this is fixed. This is fixed end. So when it is pulling up, so it has to remain in equilibrium. So from here, the reaction force is also, it is holding up in the downward direction. So near the edges, for example, up to this length, and from here up to this length, clearly you can see that some localized deformation is there. Some localized deformation is there. Some localized, and only after some distance, for example, here to here, the lines are exactly parallel. Up to some distance, there has been some localized deformation, and after some distance only, from the above also, from the below also, after some distance only, the lines are perfectly parallel to each other. So what does it mean? It means that the formula, that is their average normal stress, is equal to P by A. This is the average normal stress, and sigma is constant throughout the section. Sigma is what? It is constant throughout the cross section. So I cannot apply this formula in the regions which is nearer to the application of load. So this is Saint-Venant's principle, that we should ignore the localized deformations near the application of load. Why? Because if I show you a clearer image, then you can see that nearer to the applied load P, there is this section AA. So near AA, the stress distribution is not so even. If you see a step, one step below, then there is section BB. Clearly here also there is the load distribution is not even. Here also it is not even. And at section C, it is somewhat better. Even load, stress distribution is there. So at section C only, I can apply sigma average equal to P by A, and over here I will not be able to apply P by A. This is called as Saint-Venant's principle. Okay. Okay, so this is just a basic knowledge for your interview that I have given. Now my dear friends, let us study the tensile test. Why do I need to teach you tensile test? And I'll not get into the very much depth of this, but I need to tell you, just because I need to explain you how the Hooke's law of elasticity has come into picture. So my dear friends, what is the tensile test? I'll tell you what is the purpose of doing tensile test. We have to know the mechanical properties of the material. Okay, and more than that also, we have to know that first of all, mechanical properties mein strength comes into picture. You want to know that how much the material is resisting before failure. That strength value you need to know. Up till what strength you can apply load on the material, that thing is needed. And most importantly, you need to know the relationship between stress and strain. My dear friends, we have studied normal stress, we have studied normal strain, but till now I have not been able to establish a relationship between the two. So the relationship is established with the help of tensile test. This is the purpose of doing tensile test, and these are all experiments in nature. Experiments have been done on different material, and then only the data has been presented to you. For example, if you say that the ultimate tensile or the yield point of certain material is 250 megapascal, so it has been obtained from experiments. And what is the purpose? This I have told you. Now this tensile test is done on mild steel. Why? Because steel is the material which is used in so much in common. Its use is very much common across the world. So that's why on steel we learn the basic stress strain curve. Basically mild steel is there. Now what is done? You can clearly see that 2 points have been marked on the specimen, and the distance between those 2 points is called the gauge length. Okay, so diameter 0.5 inch is taken. There is a standard specimen. This is the dimension of a standard specimen. This is the dimension of a standard specimen. Okay, and on this only we will be conducting the tensile test. Okay. Now my dear friends, quickly I'll show you what is the graph all about. Quickly, see, it's a theoretical topic, so you can also read by own and you can understand it, but quickly I will explain you the the important points. So first of all, the above curve that you are seeing over here, the blue color curve, it is the true stress strain curve, and the curve which you are seeing the below, which is something like this, like this it is the curve. So this curve is known as conventional stress strain curve. So I'll tell you first that what is conventional stress strain curve. In conventional stress strain curve, there are two things. One is the nominal stress. One is the nominal stress and one is the nominal strain. Nominal strain. So nominal stress is P by A naught. That is, P is the applied load and A naught is the original cross section area. And in case of nominal strain, it is change in, the change in length divided by the actual length or the original length. Original length. And this is the relationship between, let's say, the nominal stress is sigma and the nominal strain is epsilon. So the relationship between sigma and epsilon is being plotted on conventional stress strain curve. And that is the relation that you are seeing over here. And why true stress? In true stress, we replace the original area by actual area and we replace the original length by actual length. And whenever you know that whenever a material is subjected to tensile test, you can imagine that the area keeps on decreasing. So when area keeps on decreasing, stress equal to force by area. So when something in the denominator decreases, the denominator actual value increases, and that is why the true stress strain curve you are seeing that it is above the conventional stress strain curve because the stress increases. Also one more thing, in strength of materials we will be basically dealing with the conventional stress strain curve, and true stress strain curve you people will study in production, right? So production mein you will study true stress strain curve, that is sigma is equal to k epsilon to the power n. Now my dear friends, let me explain you that what are the different parts of the region. So initially you will see that initially there is a relation of sigma and epsilon. It is a straight line is there. So this straight line is where the linear relationship between stress and strain is there, and this is the topmost point of it is proportional limit. Good afternoon, Atul. So the topmost point of the relationship is, or the line is, proportional limit. What is proportional? That means linear relationship is established between stress and strain. Also, if you leave the loading, if you remove the loading, the material is fully capable of returning to its original position. If you increase the load slightly, what will happen? There is after proportionality limit, the curve will follow a slightly bent structure. So this is what I am explaining, Atul, that what is the difference between proportional limit and elastic limit. So for example, this is the proportional limit and over here straight line is there, so this is proportional limit, and just after the proportional limit the curve will be slightly bent. It will be a curve kind of nature, the graph that it shows. And this is the topmost point of this is elastic limit. So the only difference between proportional limit and elastic limit is till proportional limit it will be a straight line. After proportional limit it will follow a curve. But mind it that till elastic limit your material is fully capable of coming back to its original position if you remove the load. right? In materials such as steel, these points are almost same. It is very hard to identify that what is the elastic limit of steel and what is the elastic proportionality limit of steel. That is why both are taken to be same. So it's very difficult. So anyway, that is not the issue. After elastic limit, what happens? Your material will start to deform, and that too permanently. Once the material crosses the elastic limit, it will be deforming plastically without any application of load. Even if you don't apply load, the material will continue to deform, and that is known as the plastic region. That is known as the plastic region or yielding region that you are seeing. So this is known as the elastic region. Elastic region. After this is known as the plastic region. Why plastic region? Because permanent deformation will take place without the application of load, and this is kind of a flat. It will be, the curve will be flat, right? And now, Pragvit, I'll come to your doubt once we study, will discuss Hooke's law. It is the establishment of Hooke's law. Then I will discuss your doubt. But first, let me explain you the graph properly. Okay. So after the elastic limit, this elastic limit where the material deforms permanently, this is called as the plastic region. After that, what happens? That if you keep on applying load, the strength of the material increases. The strength of the material increases, and this is known as strain hardening region. It is known as strain hardening region. Basically, the production processes, the metal forming processes deals with the strain hardening region. In this, the strength of the material increases. The strength of the material, the residual stresses increases on the surface of the material. So I'm not going into the very detail of how strain hardening takes place, all those things, but just sufficient to know that this region is strain hardening, and the strength of the material greatly increases in this region. And the topmost point, the maximum limit, is known as the ultimate stress, and after that what happens? The material begins to fracture, and this is known as the necking region. This is known as the necking region. Till strain hardening region, your sectional area will continue to decrease, but in necking region it decreases, it fails all of a sudden. When it will decrease and when it will fail, you don't know. So that is the feature of the necking region. So I know, means no need to go in very much detail, you can read it on your own, but just I have covered the main important points, that what is the features, what are the features of the graph. But why I am explaining you? Because we are right now concerned about the proportionality region or the elastic region. Why? Because this is important in the development of Hooke's law of elasticity, right? So you can see over here, that for mild steel, this is the stress strain curve that is being shown over here, and all these things I have discussed. Now my dear friends, in the proportionality limit, in the elastic region, region or till proportionality limit, in the elastic region or till the proportionality limit, it has been seen that strain is directly proportional to how much stress you keep on applying, and sigma is equal to, directly coming to the relationship, sigma is equal to Young's modulus into epsilon. Sigma is equal to Young's modulus. So what is E? E is nothing but the Young's modulus of elasticity. Young's modulus of elasticity. And this is also the slope of the stress strain curve. Also it is the slope of stress strain curve. stress strain curve. And mind it, we are dealing with the conventional stress strain diagram. Conventional stress strain diagram. In case of true strain, in case of true stress strain diagram, the relationship will become something like this. K epsilon to the power n, where n is the strain hardening exponent. All those things is not needed here. This relation you will study in production, and this relationship we use in SOM. So clearly you can see that why we are able to use this relationship, because the material does not generally crosses the proportionality limit. Whatever loading we apply, we keep till proportionality limit, or you can say elastic limit, because both are same points only. We don't cross that region. That's why we are able to use this relationship very easily. But when it comes to manufacturing processes, you have to deform the material, na? Plastic deformation will take place. So that is why you cannot use this relation. You have to follow that true stress strain relationship. Is this thing clear? This thing you people are able to understand? Okay. So my dear friends, this is Hooke's law, and you know there is Hooke's law in case of spring also. So same, Robert Hooke only gave the theory for spring also here, and in here also he gave. Okay. Now my dear friends, let us come to the topic of elastic deformation of an axially loaded member. Elastic deformation of an axially loaded member. So now you know the relationship. When I say delta equal to, you will say PL by AE. So that relation only I am trying to find out that how it is coming, and this we will also see with the help of one example. So what I have taken a varying cross section. I have taken into account. I have taken a material whose section keeps on varying cross section I have taken. So at every x if the cross section is varying, so I can write here A as a function of x. X, you can see that the distance is from the left hand. Achha, also generally what will happen, your load is generally constant, but here I will take that it is varying. So varying load also I am taking into account. Varying external load is also I am taking into account. That means with every x the load changes. It can be an example of gravity. It can be an example where gravity is applying, something is hanging. So when gravity applies force on the body, at every section the force changes. So it can be a case of self weight also. Example, self weight. Example, self weight. Force deformation due to self weight, if you are trying to find out, this can be a case. What is my objective, my dear friends? What is the aim over here? The aim is, what is the aim? The aim is I have to find the relative displacement. I have to find the relative displacement of one end of the bar, with respect to the other end of the bar, with respect to the other end of the bar. This is the objective. So now my dear friends, can I directly apply the relation sigma is equal to P by A or sigma is equal to stress by strain? No, matlab sigma is equal to P by A, directly I cannot apply. Why I cannot apply? Because the area at every section is changing. The load is changing. So when something keeps on changing, I need to take the help of integration. I need to take a small strip and then only I have to analyze it. And after that I can apply integration and get the answer. So what I will do, I will take a small section over here. I'll take a small section over here. Let's say the distance, the length of this small section will be dx. So what is the purpose of taking a small section? Because I know that in the section is so small, the length is so small that I can assume that the area is not changing in that cross section. So on this material, the load P, which is a function of x, is acting. And this load causes a deformation of the, this is small, causes a deformation something like this, which I have shown by the dotted. So let's say the deformation is delta. The deformation is delta. Okay, the deformation is delta. So for this element I can write what? From, means if the loading is within proportionality limit, I can write sigma is equal to Young's modulus into epsilon I can write, and also I can write sigma is equal to P of x divided by A of x. Yes or no? And further going on, Young's modulus into what is strain? Strain is delta, change in length by original length. Change in length by original length I can find out. Yes or no? Let's say this is del L. For simplicity, I am writing del L. Del L I am writing, the small change I am writing as del L. So both the sigma you can, equate it. So let me take on to the next page, no issues. So sigma is equal to Young's modulus into epsilon and Young's modulus into del L by dx, and also sigma is equal to P of x by A of x. So if I equate both the sigma, if I equate both the sigmas, so d of L is equal to Px dx by A of x into E. So that dl was due to, it was only on that particular small element. So for the entire element, for the entire length of the unit or the entire bar, you have to integrate del L from 0 to L, or if you can simply write integration dl, and this you have to integrate. So integration dl, so Px dx by Ax, and E dx is integrated from 0 to L. So this will give you the total deformation. This will give you the total deformation L, integration of 0 to L, let me change it, L total, the total, or I can write delta total, deformation total I can write, delta total I can write. So P of x dx by Ax into E, right? So why I have given this? Because this is the basics from where the formula keeps on coming. This is the basic. Now after this, for example, you know that delta total is integration 0 to L Px dx by Ax into E. Now if I keep over here, generally now problems that you will face, generally what happens, if the load applied, if P applied and area are constant, that is not changing, area constant, that means prismatic bars you have taken and where load applied is constant. So P and A you can simply take it out, na? So in that case the formula will reduce to PL by A. The formula will reduce to PL by A. So both the things we should keep in mind. Both the things we should keep in mind. This is also is needed, this is also needed. Now you know that okay, I can very easily apply this and this whenever is the need. So now I will do a question which will require the usage of this formula. This usage formula you can very easily find out, or you can do it so many things easily, so many times you have solved using this formula, and this will cause you no harm. But I will give you an example where it will be crystal clear that how the first formula is coming to picture. Please read the question once. Please read the question. Please read the question once. Please read the question. Okay. So the question says that a member is made from a material that has a specific weight gamma and modulus of elasticity E. If it is in the form of a cone having dimensions as shown, determine how far its end is displaced due to gravity when it is suspended in the vertical position. So let's say this is the fixed end that we are talking about. This end is fixed and it is hanging from some wall. Okay. The length is, the height of this cone is L and the radius is R0. So can you directly apply PL by AE? My question to you is, can we directly apply PL by AE? No, I cannot apply. Why? Because at every length, at every with increase in x or the height, the cross section is changing. So I cannot apply. Number one. Number two, the load is also not constant. The load is also not constant because it is, the deformation will be due to weight, and that is not constant. At every section the weight is changing. For example, if you take this section, so at this section this much of cone is pulling, but if you go slightly above, the more cone, some more cone is added, and that entire cone after this is pulling the section above. So that means the load is changing and the area is also changing. So both are changing. So what I have to do, whenever something changes, we cannot apply it directly, we have to take element and then only we can further proceed. So what I will do, let us take this element. Let us take this element. At this section, at height y, I'll be analyzing it. At height y, I'll be analyzing it. So let's say I've taken a cone at height y. Is it clear? The radius of this is x, and I have taken at a free end y. I am taking at a free from a free end y at y distance. So this much I'm analyzing the element at free height y, and what is its impact? The weight will be applied through this. So this much force is applied on this section. What I'm trying to find out, that this small cone that I've taken below this section, that much of force is applicable at this section. So what it will give me? It will give me something P at a distance of y, that is the varying load. Then I will also get area which is at the section, and then I will find the delta for that small section. This thing you people are able to understand? Okay. Now from the concept of similarity, can I write y by L is equal to x by r naught? This is x, this is y, this is r naught. So y is equal to xl by r naught. The radius at this section is x. So if I find what is the volume of this element, volume of this element, so you will write what is the volume of this element. So for the cone it is what? 1 by 3 pi r square h. So pi radius square h. So 1 by 3 pi x square, and what is y? Y is nothing to xl by r naught. So xl by r naught. Okay. Pi x cube L by 3 r naught. And what is the load, or what is the P at y? That means this is the volume of that element. So actually the load applied is a specific weight into the volume of this element, volume or elemental volume, or elemental volume. So specific weight is what? Gamma. The specific weight given is gamma. Yes or no? And it is pi x cube L by 3 r naught. So pi gamma x cube L by 3 r naught. Is it clear till now? Is it clear till now? Okay. So one thing is there, I have taken the distance from the base as y. Okay. So finally I have to integrate from 0 to L. So I think it's better if we write x as a terms of y. It will be better if I keep in terms of y. Okay. So this I can do. It will be better because I have taken at a distance of y, and finally I need to integrate from 0 to L only, right? So if I means, that means every term should be in terms of y. That would be better. So what we will do a small change over here. We will do a small change over here. Just a minute. We will do a small change over here. Y we will keep everything in terms of y. We will keep everything in terms of y. That would be easier for us. So pi x is what? X will be gamma, y r naught by L. Y r naught by L. Y r naught by L. So y r naught by L square into y. This would be easier, yes. So pi r naught square by 3 L square y cube. Okay, and specific weight is gamma into the elemental volume is pi r naught square by 3 L square into y cube. Don't get confused between gamma and y. So this is better, I think. Please check. This is better. This is better. And what is the elemental area? That means area at x. So area of the cross section is what? Area of the cross section. So area of the cross section is this one. So what is the cross sectional area? Pi x square. Pi x square is the cross sectional area. So pi x square is the cross sectional area. So what is x? X is nothing but y r naught by L. Y r naught by L. Pi y square r naught square by L square. Is it clear? Is it clear? So my dear friends, what we have found out that I have got the varying area, I have got the varying load, and at that section what I can do, so now delta formula, the original formula was what? Integration between 0 to L varying load into dy divided by A of y into epsilon. A of y into epsilon. So elemental area that we have taken, so varying area I have written, E I have written, P of I, so P, this is also we have found out, this is also we have found out, this we know, and dy we know. This thing is clear. So on the elemental that we have taken over here of dy, on the element that we have taken over here dy, what is the weight? The weight is nothing but P of y. What is the varying cross section? That is A of x, A of y you can say, and the length is dy. So on that, what will be the elemental pull? What will be the elemental deformation? What will be the elemental deformation? The elemental deformation is this one. And then when you substitute all the given, then when you substitute all the given, so Py whatever we have calculated, so that is y pi r naught square. So I am just writing it. It's simple integration after this. It's simple integration after this. It's simple integration after this. So when you solve this, you will be getting gamma by 3e 0 to L y dy, and finally you will be getting gamma L square by 6e. Finally you will be getting gamma. Pragyabrat, see, here I have written ax, but it is better if you write ay. Why ay? Yes, it is very good question. It is just a mistake of denoting. So it is a of y. Why a of y? Because at a distance of y we are denoting the area. Got it? At a distance of y we are finding the area. So that means it is better to write a of y. So what is the radius at y distance? It is x. So area is pi x square. Clear? Better it is a of y. Clear? At a distance of y, see, generally what happens, this distance we take as x at a distance of x, but I have taken at y. So that means a of y is a better way to denote it. Okay. So I'll quickly explain you that what we have done in this question. We have got the answer. The answer is what? Gamma L square by 6e, where gamma is the specific weight. That is weight per unit volume. L is the original length. Of the bar. And E is the Young's modulus of elasticity. So I'll quickly explain you what I have done in this question so that no doubt remains in this question. See, just a minute. This is the cone attached. In 1 or 2 minutes, I will briefly, brief you through the question. This was the cone attached. Let's say hangings from somewhere. At every point, question was, what is the deformation due to the self weight? What is the deformation due to gravity? Gravity means self weight. When it is hanging at this position, you can clearly see that the area is changing at every cross section, number 1. Number 2, the force applied at every section is also changing. At every section, the weight which pulls down any section is changing. So that means I have to go through the process of integration. For integration, we take an element, a small element. So that small element I have taken is dy, of dy length. Of dy length, I have taken a small element, something like this. This is dy. On this, I need to see that how much. This dy is at a distance y from the free end. From the free end, it is very easy to analyze, na? Okay. So on this small element, the force P at a distance of y is acting. And the element is so small, this is so small that the cross section will be constant throughout this dy. The radius is x. So what is the area? Pi x square. The cross sectional area is pi x square. I need to find P of I. For P of I, for weight, it is specific weight into elemental volume. So For weight, now see very clearly, you want to find the external load on this element. Now what is the external load? The weight which is applied by this entire small cone. The weight that is applied by this much of cone, this cone that you are seeing, the weight of this cone below the section, below this section, that weight is the pulling force. So specific weight you know, and if you find the volume of this cone, I can multiply with a specific weight and get the load. Load on what? Load on this small section that I have taken. Now P of I directly you cannot take W into T. Yes, it will act through the CG. Definitely it will act through the CG. 100% it will act through the CG. But we have to ultimately give the answer in terms of the variables that is given na. Whatever parameters are given to you. So parameters is given is a specific weight which is constant for the material. So specific weight is there. So if you only multiply the volume of the element, I will be getting the entire P of I. P of I is nothing but the weight. Yes, correct. Acha, WT means weight you have written. Correct. P of I is the weight. 100%. Very good. Yes. And it acts through the CG. 100% correct. Yes. So that is what I am trying to find out. The weight of this small element is only what is the Py. Correct. The weight only I am trying to find out. Correct. So specific weight is here. So after that, whatever I have done, ultimately the Py that it is there, it is the weight of the small cone below the cross section, below the dy element, below the dy. After that means mathematics you have seen. So once I have known Py, once I found Ay, once you find Ay, once you find Py, finally I have substituted that. Now on that dy, what is the element? What is the elongation? Let's say the elongation is delta. So small delta is this. For final you have to integrate, and after integration you get the answer. So I hope the approach is clear. I hope I am able to explain myself over here, and in case of still any doubt, you can leave your comments in the chat section. So today what did we do? Today I have explained you today we have started with this question, normal stress, normal strain. Then we discussed Saint-Venant's principle. What is Saint-Venant's principle? That near the application of the load, we ignore the localized deformations, and this formula sigma equal to P by A is only applicable after some distance from the application of load. Then tensile test, and what are the features, basic features of the curve? What is proportionality limit, elastic limit? In strength of materials, we will be there within proportionality limit only. In production subject, you deal with this after the proportionality limit, the strain hardening region. So nominal stress, nominal strain, the basic features. This relation is applicable only till, that is the Hooke's law of elasticity is applicable only till the proportionality limit. This is applicable in the strain hardening region, in the plastic region, which is there in production, manufacturing subject. We will not use this relation over in strength of materials. Finally, the elastic deformation of axially loaded bar. This is I have explained you. using different varying load and varying cross sections, and finally I have solved this question so that you get a clear picture that how this formula is being used, right? So with this we end our today's session, my dear friends, and if you are liking the session, if you are regularly following the sessions, so you can leave your valuable comments. You can like the video, you can leave your valuable comments. In case of any doubt also, you can leave your doubt, I will answer it personally. And in case you are finding this useful, so you can share it among your friends. So the friend who is preparing at home for 25, or if he wants to clear the fundamentals of SOM, this will be useful for him or her. So with this we end the session. Keep studying, keep revising, take care, God bless.